Hi guys, welcome back here at the EC Engineering tutorial. We will just continue our discussion on basic soil water relation. So we'll proceed on infiltration. Okay, so if it talks about infiltration, this is the process by which the water enters into the soil. So the intake or the infiltration rate is the speed at which the water can be taken into soil during an irrigation or rainfall event. So bali yung makikita natin dito na yung x-axis represents the time in minutes and we have this uh, infiltration rate in y. So makikita natin na over time nagdi-decrease yung infiltration rate, no? And at some point here, parang nagiging constant na yung rate, no? Approximately. And so, habang nagdi-decrease yung infiltration rate, makikita din natin na yung cumulative infiltration increases, no? Based on graph. So, during the initial condition, when the soil water is dry, the infiltration rate is high and decreases with time and tends to approach a constant rate, no? So this constant rate of infiltration is referred to as the basic infiltration rate or the final infiltration capacity or simply the infiltration capacity of the soil. So the downward movement of the infiltrated water through the soil profile is known as percolation. So the accumulated infiltration or the cumulative infiltration is the total quantity of the water infiltrated into the soil in a given time. So the graph shows both infiltration rate curve and accumulated or cumulative infiltration curve. Infiltration rate may change with respect to the location, the time or season, and the initial soil moisture content. So a range of basic infiltration rate for four common soil texture is presented in this table. So we have this soil texture and then meron tayo ditong basic infiltration rate in inches per hour. No? So for fine sand, yung range ng infiltration rate is around 0.5 to 0.75 inches per hour. Yung sandy loam is 0.35 to 0.5, yung silt loam is 0.25 to 0.4, while yung clay is 0.10 to 0.2. So why infiltration rate decreases with time? So here's the answer, no? So the decrease in the infiltration rate results from the decrease in the metric suction gradient. So this constituting one of the forces drawing water into the soil, which occurs as infiltration proceeds. So if the surface of an initial dry soil is suddenly saturated, the metric gradient acting in the surface layer is at first very steep. No? So as the wetted zone deepens, however, this gradient is reduced. No? Furthermore, as the thickness of the wetted soil increases, the metric suction gradient eventually tends to become vanishingly small. So finally, the infiltration rate reaches the steady state condition. So the decrease in the infiltration rate from initial high rate can in some cases result from gradual deterioration of the soil structure and consequent partial sealing of the profile by the formation of the dense surface crust or form the detachment and migration of the four blocking particles or swelling of the clay or air entrapment. So these are the infiltration rate we use. So in the field of irrigation, we use the Kostyakov equation. Okay. So, bali, ito yun, no? So, a double ring infiltrometer test was conducted prior to an irrigation event and the data recorded are given in given in the table as shown here, no? We have this time and the cumulative infiltration. So, to determine the parameters in the Kostyakov infiltration equation, so, ito yan, no? So, we have this time, we have this cumulative infiltration. We take the log of time and then we take the log of z, no? And then we can now compute for the predicted value of z. So, bali, in equation form, we have this log of z which is negative 0.502 plus 0.773 log of t. Or yung z in terms of exponential equation, we have 0.315 log of t raised to the power of 0.773. So ito naman yung graph niya. We have this cumulative infiltration rate and we have this Z model. So to overcome the restriction of the original Kostyakov infiltration equation, it was modified to include the steady state infiltration term. So bali yung nangyari sa formula is ito na, no? For the equation of Z and for the equation of I. So yung E tsaka B dyan, yun yung mga parameters, while yung C is yan yung steady state infiltration rate. So pag sinabi natin steady infiltration rate, it can be determined from infiltration measurement when infiltration rate approaches to near steady state condition. So we have also factors affecting the infiltration. So the major factors influencing the infiltration include the initial soil moisture content, the soil surface condition, the hydraulic conductivity of the soil profile, the texture, the porosity, the degree of swelling of soil colloids, the organic matter and the vegetative cover, duration of irrigation or the rainfall, and viscosity of water. So initial moisture content have a direct effect on the infiltration rate and the total amount of infiltration. Infiltration decreases with the increase in the initial soil moisture content. Infiltration rate or the total infiltration increases as permeability and porosity increases. Cultivation increases the infiltration by improving the porosity. Infiltration rates are normally lower in heavy textured soil than in light na textured soil. So vegetation improves the infiltration of soil. So ito yan, no? Ito yung mga graph natin. We have this x-axis time and we have this infiltration rate. So nag-decrease sila, no? And we have this cumulative infiltration rate for 3 soil particles. So while yung cumulative is also increasing. So meron din tayong tinatawag na soil water retention. So makikita natin dito, we have this for example, ito yung soil specimen natin. Ito yung field capacity, no? Makikita natin, ito yung mga solid particles, yan. And then we have this water tsaka air, no? Dito naman sa permanent wilting point, halos air na, no? Wala nang tubig. May tubig, pero itong black na part, yan yung tubig. But that is unavailable to plants, no? Hindi na kayang kunin nung plants yan. Okay, so despite the belief that soil absorbs water, water is actually held in the soil in two ways, no? As a film coating on soil particles and in the pore space between particles. So when water infiltrates into the soil from either precipitation or irrigation, the pore spaces are nearly filled with water. So during and immediately after a rain or irrigation, the greatest vertical movement of the water occurs in the soil. So after this initial movement, as the soil reaches the filled capacity, water movement continues due to gravity and capillary action. So capillary action is important for retaining water in the soil particle. So ganun, no? So we have this soil water relation. So ito yung anyway, pag magko-compute tayo ng soil related sa soil water, yung mga problems, magagamit natin itong FC, which is the field capacity, and the PWP, which is the permanent wilting point. Okay, so ayan, no? So small tubes or capillary tubes can be used to illustrate the capillary action, no? So like soil pores, capillary tubes come in different diameters. When one end of the capillary tube is placed in water rise in tube because the capillary action is stronger than the pull of gravity. So because capillary action is stronger than gravity, water will never completely drain through the soil profile. So some water will always be held in the soil profile. Okay. So water rises farther in small capillary tubes such as shown here. So pag large naman yung diameter ng tube natin, so mas maliit yung akyat ng tubig, no? So in terms of mga pore spaces sa soil natin, so kung maliit yung tiny yung mga small mga voids sa soil natin, so medyo malaki yung capillary niya. Larger capillary tubes corresponds to a coarser texture soil such as sands, have a large pores, and smaller capillary tubes correspond to the finer texture soils such as clay having a small pores. So capillary action can best be explained with an illustration below. So four tubes containing soil of different texture are placed upright in a tub of water. So the water rises highest in clay, such as shown here, because it has smallest pores. So the clay soil exerts the greatest capillary action on water, while the fine sand having the larger pores exerts the less capillary force. Okay, such as shown here. So the capillary action or the tension which holds water in the soil is most important to plant growth. No? Small pores hold water with more tension or negative pressure than larger pores. So as soil dries, the tension of the remaining water increases. So plants can extract less and less water as the soil water tension increases. So yun lang, no? So yeah, hindi maganda pag clay yung soil. Okay, so ito yung mga available water capacity based on soil texture in inches per foot of depth. So again, we have these textural classes: coarse sand, fine sand, loam sand, sandy loam, silt loam, silty clay loam, silty clay, and clay. So as soil water storage characteristics are very important for irrigation management, so since the size and the number of pores in soils are directly related to soil texture. So soil texture is the indicator for the amount of water a soil can hold. So we are guided by this table, which can be used to determine the amount of available soil water that a soil of a given texture will hold. So this is what we call the EWC, no, or the available water capacity. Ayan. So we have these soil water components in apat na common soil types. So we have this, the black one is the readily available water. So ito yung kinukuha ng plants natin, no? And then we have this less available water, no? And we have this unavailable water that is below the wilting point. So makikita mo dito na pag clay, so sobrang malaki yung uh, portion ng unavailable water compared dito sa fine sand, no? At saka yung sa mga loam natin. Okay? So knowing the soil water content in the crop's active root zone and the available water capacity is the key to applying the right amount of irrigation at the right time, no? That is what we call irrigation scheduling, no? So soil water holding characteristics are important for irrigation system selection, irrigation scheduling, crop selection, and maintaining the groundwater quality. So since soil can hold only so much water exists or gravitational water moves out of the crop root zone toward the groundwater table, and many nutrients and chemicals move with the water and can eventually be found in the groundwater, so thereby degrading the quality of this resource. Okay, so in the next video, we'll be discussing the classes of soil water. Okay, so that's it. See you in the next video.